It's a great pleasure to introduce one of our ongoing projects and one of the tools that we're developing in the framework of XAIDA. And it's really motivated by the fact that in recent months and years, we've seen a series of unprecedented extremes, some of them already shown by Sarah in her introduction. And one of the questions is, can we anticipate these extremes? Can we do we have tools to better prepare for this? And one impressive examples that also came as a surprise for many scientists was what we call record-shattering Pacific Northwest heat wave, which literally broke previous margins by very large previous records by very large margins, more than 5 degrees warmer across substantial regions, reaching maximum temperature 49.6 degrees Celsius in Canada. So this is challenging for the existing methods to deal with, but it was not the only event. We had other events, some in the middle of nowhere in Antarctica. It's mostly the weather geeks that noticed it. It was 40 degrees warmer than average during the typical season. Others in densely populated regions like London, first time 40 degrees, which is substantially warmer than anything observed in the very long record that we have in the southern UK. But also other aspects were affected. Heavy rainfall caused flooding in the R Delta. This is a paper by Jordis Stradowski, who's actually also on the call. And it shows that even in precipitation, we can have events that you would not expect based on the observational record up to that date if you only look locally. That goes on in other spheres. We had a hurricane, tropical cyclone earlier this year, reaching Category 5 along the Mexican coast. The Pacific coast has never happened in this location in the observational record. The ocean reached temperatures of unprecedented levels also in the Mediterranean. This is important because typically we have a sea breeze coming to the densely populated Mediterranean coast. If the water is very warm, you end up getting very humid and warm air that is advected to these already very hot places. And even glaciers melted at unprecedented rates. So one of the questions is, if we had been asked by the city of Vancouver, the province of British Columbia in the year before, could we as climate scientists have pointed out the fact that we had that we should be expecting, not in a weather forecast type of idea, but rather a year ahead, if someone had asked, what is the worst case we should be preparing for in the next 10 years or so? Could we have been pointing out the fact that a heat wave 5 degrees warmer than anything previously observed is possible? So this is one of the questions we are addressed in the framework of this program, of this project, XAIDA. And one thing that we did is we ran a climate model many times. This is already quite a traditional method that we can now afford to do. The problem in reality, we only have one observation, right? And this is relatively short in many places, particularly in today's climate, which is now nearly 1.3 degrees warmer on global average than it used to be. We only have about 10 years that are representative of that climate. So climate models are a good tool to explore, to give us more of what we could be expecting in the coming decade or so. So we did this for the Pacific Northwest region, and this black line, the solid black line, is the temperature level that was reached. And you see here, I showed you one of the worst cases that we got in 1,000 years of climate model simulation. You see, we got close, but not quite reached the level of this very extreme heat wave. So we thought, okay, we need to have tools that go beyond this, because we simply cannot afford to run this fully coupled Earth system model for 100,000 years or so. And we're really interested in the very extreme case, particularly because maybe also the models tend to be a little bit too conservative. So we developed a method that we called Ensemble Boosting, which is based on the idea of the butterfly effect. And I try to illustrate this. I'm not sure whether you can see it through Zoom. So these are two simulations that only differ by a tiny, tiny perturbation. Initially, you don't see any difference for about 5 to 10 days because the perturbation we add is extremely small, but then it grows in time because we're looking at the chaotic weather system. And then we could produce many, many trajectories that the weather could have taken in a specific case. And that's what I'm showing you here. And you see, suddenly we get heat waves that go substantially beyond what has been observed in the Pacific Northwest in 2021. And the nice thing about this method is that this is computationally relatively cheap, and it gives us a time trajectory. It gives us also a spatial field that we can try to look and understand why in the model world did we have such an extreme case, and by this we could also hopefully understand whether we should really be expecting such an event in the real world. We also repeated this now for places where we haven't seen such an event yet. Greater Chicago is one of the places where we have not seen a distinct upward trend in the heat wave intensity. The question is, how much worse could it get? And according to our method, it could get a lot worse. This is one of the places where we haven't seen much of a trend, but according to this method, we could have heat waves that go substantially beyond what we've been so far seeing, because I think primarily by luck, we had not been seeing a very extreme case in this particular region. And if we compare this to the existing case, to one of the worst cases that has been observed, you see the magnitude of this event that our climate model produces in this method, which is truly a worst case. It's not a likely case, but a worst case scenario is substantially beyond the one that we've seen in the past. So what I'm showing you here is based on a global climate model. So it's a relatively coarse solution, and some of you are working on the level of cities. So this is a challenging task now to translate, and this is what my colleagues are also going to talk about, to translate it to the city level, because we know, and this is now shown already for Paris, that my colleagues are going to talk about, that in the cities, particularly at night, the temperatures are substantially warmer in some places, and usually exactly those places where we have dense population. This is not only for heat a challenge, it's also for heavy precipitation. This is a place of a Swiss city, Lausanne, which got one of the worst heavy rainfall in 10 minutes. So it was 41 millimeters precipitation in 10 minutes. It's really inconceivable. It was a very local event. The city surfaces made it even worse. So cities are specifically, not only do they have a high exposure, but also particularly vulnerable due to their specific urban surfaces. So I'm concluding here that looking back at the observational record, if we do this locally only, this is a good start, but often not enough to plan for the coming decades. So we need to prepare for events that go substantially beyond what we've seen. And one of the reasons is that we're going through a period of a very, very rapid warming on the global, but also at the regional level. And Ensemble Boosting, the one I'm showing you, is one of the tasks, one of the tools that we can use for this. But I'm convinced that we need a whole range of different methods, and my colleagues Robert and Pascal are going to introduce some others, and I think the multitude of them is really what's giving us confidence and what we can base our planning on. Thank you.